everyone. Our next step in our progression of learning all the derivative shortcuts that we need is to introduce a few more functions. We're really almost done. Chain rule was a really big one. So in this section, we're going to introduce the shortcuts for logs and inverse trig functions. And then our next step from here is really to change things up a little bit. It's to start to look at a little bit more flexible way to think about taking derivatives. That's implicit differentiation. So this is really our last big shortcut section. Okay, so we are going to use another kind of cool and different trick for finding the shortcuts for these functions. The reason these are all grouped together is because they're all inverses of other functions that we already know how to take derivatives of. So logs are inverses of exponential functions, and inverse trig functions are inverse trig functions. So here's how we're going to start. We're going to say f of x is equal to the natural log of x, and we want to find f prime of x. So using the fact that we know the inverse of the natural log of x, we're going to rewrite this. The inverse of natural log of x is e to the x, which means we can exponentiate both sides of this equation. It's the same tool we use to solve log equations. And e to the f of x is what it is, but e to the natural log of x is just x. Whenever you compose a function with its inverse, you get back x. Now that we've done this, we're going to take derivatives of both sides of the equation. And we haven't really been thinking about it that way, but that's a totally valid way to think about what we've been doing. And that's a legal step in the same way you can multiply both sides of the equation by the same thing, or square root both sides of the equation. We can take the derivative of both sides of the equation. So I'll take the derivative of e to the f of x, and I'll take the derivative of x, and if those two things were equal, their derivatives should be as well. The right-hand side's the easy one. The derivative of x with respect to x is 1. The left-hand side needs a chain rule because it's composite. So e to a power is its own derivative, so we get e to the stuff, and then the derivative of f needs to chain out. Remember that we were looking for f prime of x, and now there is an f prime of x in our equation, so we can solve for it. We can divide both sides by e to the f of x, and we now have the beginnings of the formula for f prime of x, but I don't really want f of x in there. I just want the same kind of formula as we had before, where we would say the derivative of x squared is 2x. However, I've already dealt with this problem up above. I've already said that e to the f of x is just x. Remember, f of x is the natural log, so if we take e to the natural log of x, we get x, which means our shortcut is the derivative of natural log of x is 1 over x, and I think that's kind of surprising. We do have to add one restriction on this. We haven't seen this before. We haven't had to do this. But we have a weird issue here in that natural log of x, remember, can only take inputs greater than 0. We don't have to write that down. That's a built-in feature of the natural log of x. But 1 over x can take positive or negative x values. The only one it can't take is 0. So we need to restrict the domain over here just so that it matches, so that no one's accidentally saying, oh, well, I can find the slope of the natural log function at x equals -1 just by plugging in. You can't do that because the natural log function doesn't exist. So this has a little domain restriction that we tack on just to make the domain on the two sides agree. Let's work on inverse trig in the exact same way. So if I want to find the derivative of arcsine, for example, let's let f of x equal arcsine of x, and we again want f prime of x. We want to know the derivative. So this time we would say if we take the sine of both sides, so sine of f of x, is equal to the sine of the arcsine of x, which should just give us x. So I really like this here, not just because it's a cool trick for finding these shortcuts, but actually for another reason. The type of thinking we do here is a baby step towards the thinking we'll do with implicit differentiation. So in your next section, you're going to be using this kind of thinking where you take the derivative of both sides and you see what happens and you solve for your derivative. So here, if I take the derivative with respect to x of both sides, I get 1 on the right-hand side. On the left-hand side, I need a chain rule. The derivative of sine is cosine. I leave f of x alone, but then I chain out the derivative of x. So this time I'm getting f prime of x is equal to 1 over cosine of f of x. And this one is a little bit trickier than the last one to simplify, because I know that sine of f of x equals x, but I don't immediately know what cosine of f of x equals. So I'm going to start by putting that arcsine function back in for f of x so that I can look at that. And this brings us back to some trig. And we won't have to do a ton of this quarter, but it's a really good time to review it because we will have to use it for sure in 152. So we're going to have to remember a little bit of triangle stuff to figure out what this is. We don't want to just quit here. We can actually get to a reasonably nice algebraic function that doesn't have any sines or cosines in it. So if we think about triangles, arcsine of x, if I say arcsine x equals theta, I could rewrite this as x is equal to the sine of theta. So arcsine of x is the angle, represents the angle theta, whose sine is x. On a triangle, we think of sine as a ratio. So it's x over 1, and sine is opposite over hypotenuse. There are other ways to label a triangle that would make the value of sine be x, but this is the simplest, so we may as well go for it. And then what we want to know is cosine, so that's going to involve this bottom side of the triangle, and we can find that bottom side of the triangle by using the Pythagorean theorem. So I'm temporarily going to call it b for base, and I can say b squared plus x squared equals 1. So b squared is 1 minus x squared, and that means b is plus or minus the square root of 1 minus x squared. But this is a triangle, so we don't want negative side lengths. So that bottom sine is square root of 1 minus x squared. Okay, so now if I want to find the value of cosine of that angle, I need to take adjacent over hypotenuse. And that is going to give me, let me write it down here, 1 over the square root of 1 minus x squared. So cosine of theta is going to be square root of 1 minus x squared adjacent over hypotenuse, which means in the denominator I just need the square root of 1 minus x squared. And that is your arcsine shortcut. So the derivative of arcsine is 1 over the square root of 1 minus x squared. Remember that inverse sine can be written as arcsine or sine to the negative 1. Sine to the negative 1 doesn't actually mean to the negative 1, it means inverse. So either of those notations, same shortcut, memorize this one. I'm just going to give you the last two inverse trig functions, but I encourage you to think about and review this triangle stuff a little bit. And if you want to see it, just let me know. I'd happily give that to you, but I don't know if you want to watch two more right now. So we've added the natural log shortcut. We've just done the inverse sine shortcut. The other two are arc cosine of x, or inverse cosine of x, and arctangent of x. The derivative of arc cosine ends up just being negative 1 over the square root of 1 minus x squared. So arcsine and arc cosine give you the exact same expression. It's just that once again the co gives you a negative. And then arctan actually works out, I think, a little bit nicer even. It doesn't have a square root at all, and it ends up being 1 over 1 plus x squared. So it's not only, it doesn't have a square root, it also becomes a plus in the middle there. So you've got 4 new shortcuts to memorize for this section. So add them to flashcards or something and start working on those. We won't do the arcsecant, arccosecant, any of those, just arcsine, arccosine, arctangent.